everything looks still. The buildings, the ocean, even you. But the entire planet is already moving. Near the equator, Earth's rotation carries you eastward faster than most passenger jets ever fly. Here, the surface moves about 465 meters every second, over 1,000 miles per hour. So we anchor you directly to the bunker. Without restraints, this experiment could end almost instantly. Your body, the atmosphere, and every ocean already share the planet's enormous eastward momentum. 0. Earth stops rotating, but your body keeps the velocity it had 1 instant earlier. Anything not forced to stop keeps moving until another force finally changes its motion. And your body isn't alone. The atmosphere was rotating too, and it keeps moving eastward. Near the equator, the initial speed difference approaches 465 meters every second. This isn't ordinary wind. The initial relative speed can exceed the local speed of sound. 3 seconds in, the atmosphere starts attacking the city, tearing glass and lightweight facades away. As air moves faster, aerodynamic forces rise dramatically, overwhelming surfaces never designed for these conditions. Even heavy vehicles become vulnerable. Extreme airflow can overcome tire friction and overturn entire trucks. 5 seconds. The bunker survived your inertia. Now it must survive everything carried by the wind. But the air is already changing. Buildings and terrain drag against it, creating violent turbulence. Every tower, tree, and street transfers some atmospheric momentum back into the suddenly stationary surface. Higher above the ground, enormous layers of atmosphere are still racing east with less resistance. The first shock is over, but chaotic pressure pulses keep hammering the bunker again and again. 9 seconds. The bunker still stands, but the repeated loads are finding its weakest points. 10 seconds in, the city is buried in debris, and something far heavier is still moving offshore. Now the wind carries more than dust and glass. Large pieces of the city become projectiles. 12 seconds. Every object outside is part of the disaster, and some are hitting the bunker. Speed alone doesn't decide survival. What matters is how quickly that speed is taken away. Large vehicles and exposed infrastructure face forces far beyond anything they were originally designed to withstand. 15 seconds. The bunker still has structure, but its electrical systems are beginning to fail. Gravity hasn't disappeared. Near the equator, your effective weight would actually increase slightly after rotation stops. Rotation slightly reduces effective gravity. Remove the spin, and that small outward contribution disappears too. But the atmosphere isn't Earth's largest moving mass. Beyond the harbor, the ocean is still moving. 19 seconds. The bunker is no longer perfectly sealed. Outside damage is reaching the air inside. 20 seconds. Air attacks from above, while moving seawater begins forcing its way inland below. 21 seconds. Water escapes the harbor and starts flooding the city's lowest streets and districts. But this catastrophe isn't equally violent everywhere. Rotational surface speed is greatest at the equator. Near the poles, the ground was moving much slower, so the first inertial shock is smaller. Back near the equator, one shock absorber begins leaking. Your survival system is starting to weaken. 25 seconds. The frame still holds, but every new impact is becoming harder to absorb. Near the surface, the air is no longer one clean 1,000-mile-per-hour stream. Turbulence dominates now. 29 seconds. Floodwater finds tunnels, underpasses, and low streets that carry it farther inland. 31 seconds. One anchor bolt fails, forcing the remaining connections to carry even greater loads. 33 seconds. You're alive, but your survival system is degrading while the catastrophe continues outside. 35 seconds. Surface winds are losing momentum, but the ocean is still moving deeper inland. 36 seconds. The water reaches the bunker. Now the structure must resist both air and water. Stop Earth's rotation and the familiar Coriolis effect disappears, but existing atmospheric momentum does not. Global weather won't reorganize in seconds. The atmosphere needs much longer to redistribute its enormous momentum. And Earth's magnetic field doesn't instantly disappear. Its source lies deep within the liquid outer core. 41 seconds. Water presses directly against the bunker, producing forces far greater than moving air. 42 seconds. The damaged restraint mount begins deforming, transferring even more stress into fewer connections. 44 seconds. The largest viewport crack begins spreading, though the laminated window still holds. 45 seconds. The bunker was beside the ocean. Now the ocean is beginning to surround it. 47 seconds. The damaged mount slips, leaving almost no redundancy on one side of the frame. 48 seconds. The horizon changes. A much larger mass of displaced water is still approaching. 49 seconds. The second surge reaches land, piling into water already flooding the coastal city. 50 seconds. The bunker is no longer beside the flood. It is now inside it. 52 seconds. The door remains locked, but rising pressure forces water through its damaged seal. 54 seconds. Floodwater reaches the restraint platform, threatening the systems that kept you alive. 56 seconds. The last major anchor begins bending. One complete failure could release the entire frame. 57 seconds. The viewport disappears underwater, placing dense moving water directly against the cracked glass. 58 seconds. Air and ocean are still moving. Planet-sized momentum cannot vanish in 1 minute. 59 seconds. Another impact moves the frame. The final anchor bends farther, but somehow still holds. 60 seconds. You survived the first minute, but the catastrophe itself has barely begun. Now the real transformation begins. Oceans, atmosphere, climate, and the meaning of a day must change. Stopping Earth's spin does not stop its orbit. The planet continues racing around the sun. Without axial rotation, the familiar 24-hour day disappears, stretching toward roughly 1 orbital year. Some regions could experience months of continuous sunlight, allowing the surface far more time to heat. Then comes prolonged darkness, giving the surface far more time to lose heat and cool. Without rotation, familiar Coriolis-driven winds disappear, forcing Earth's atmosphere into a completely different circulation pattern. Rotation also creates Earth's equatorial bulge. Without it, the planet gradually trends toward greater sphericity. As Earth's shape adjusts, oceans would slowly redistribute away from the old rotational equatorial bulge. Given enough time, today's coastlines could become unrecognizable as entire ocean basins find new equilibrium. The magnetic field still wouldn't vanish instantly. Its long-term future depends on the deep geodynamo. So stopping Earth's rotation changes more than wind. It changes oceans, climate, days, and eventually geography. But none of that future matters yet. You're still here, 1 minute after the planet stopped. The bunker survived the first minute, but water keeps rising, and the structure keeps weakening. The real danger wasn't simply that Earth stopped. It was that everything else kept moving. After 60 seconds, the city is nearly unrecognizable, and the planet is nowhere near a new equilibrium. You survived Earth stopping, but inside Jupiter, there wouldn't even be solid ground beneath you.